Hello, my name is Joseph Bisham. I'm an MSc student of AI and machine learning, and my topic is learning from temporal data, where I was more focused on the temporal convolutional networks technique. Temporal data refers to a set of data points collected or recorded over a period of time. These data points are usually organized in a sequential order and are associated with specific timestamps, such as dates or times. Temporal data are prevalent in many fields, including finance, economics, meteorology, and environment science. Analyzing time series data can help to identify historical patterns, forecast future events, and make informative decisions. One of the modern techniques used for learning from temporal data are temporal convolutional networks. TCNs are a class of deep learning models that use convolutional layers to process time series data. The key concept of TCNs include 1D convolutional. TCNs use one-dimensional convolutional layers, which are specifically designed to process sequential data. The filters in these layers slide over the input sequence, learning local patterns or features in the same time series. Stacking layers. TCNs can be constructed as deep networks by stacking multiple convolutional layers. This allows the model to learn increasingly complex and abstract features from the input data. Some of the state-of-the-art techniques in the context of TCNs are multiscale TCNs. These models employ a multiscale architecture to capture patterns at different temporal scales. Multiscale TCNs can effectively learn both short-term and long-term dependencies in the data. Another one is transfer learning. Applying transfer learning techniques to TCNs can improve performance by leveraging knowledge learned from related tasks or datasets. These techniques can help the model generalize better. The application of TNCNs is huge, and there are two examples of papers that use this technique. First research paper is about time series forecasting. In this paper, the authors propose the use of temporal convolutional networks for forecasting energy-related time series data. They focus on two main energy-related applications: electricity price forecasting and wind power generation forecasting. These tasks are essential for efficient power grid management and the integration of renewable energy sources. The paper presents a comprehensive evaluation of TNCN models for these tasks, comparing their performance with other deep learning models, such as long short-term memory networks and exponential smoothing state space models. The results show that TNCNs outperform other models in the majority of the scenarios, demonstrating their effectiveness for energy-related time series forecasting. The authors also analyzed the impact of various hyperparameters and architectural choices on the performance of the TNCNs models, providing insights into how to optimize the models for different tasks. Second research paper is about satellite image classification. In this paper, the authors proposed a TNCN-based model specifically designed for handling the challenges posed by SITS data, including missing or noisy data, irregular sampling intervals, and high dimensionality. The model takes advantage of the TNCN's ability to capture complex temporal patterns and dependencies in the data. The proposed TNCN model is evaluated on several publicly available SITS datasets and compared with other state-of-the-art methods, such as convolutional neural networks and recurrent neural networks. The results show that the TNCN-based model outperforms other methods in terms of classification accuracy. There are many open questions in the TCN's research area. One of those are architecture improvements, but I want to talk now about attention mechanisms that can help the model focus on the most relevant parts of the input sequence. Further research on incorporating attention into TNCNs and understanding their impact on performance can lead to more robust models. There is an example of such paper using attention mechanisms. In the paper, the proposed model, named TCN-RSA, combines the strengths of TCNs for capturing temporal dependencies and the self-attention mechanism for adaptively weighting the importance of different timestamps in the input sequence. The residuals connection is used to facilitate the flow of information and gradients through the network, helping to mitigate the vanishing gradient problem and improve model performance. The results show that the proposed model outperforms other state-of-the-art methods, including long short-term memory networks, convolutional neural networks, and traditional TCNs in terms of prediction accuracy. Specific technical issue is adapting TCNs to handle large-scale or streaming data. The goal is to develop efficient online learning algorithms that can update the model with newly arriving data without retraining the entire model from scratch. In the context of TCNs, this can be particularly challenging due to the convolutional structure, which inherently relies on fixed-length input sequences. In traditional batch learning, the model is trained on a large dataset using stochastic gradient descent, and the model's weights are updated based on the average gradient. When dealing with streaming data, the model should be able to adapt to new data points as they arrive, making it difficult to apply the standard batch learning approach. As before, I provide one example of a research paper trying to apply a new approach to overcome these issues. The authors of the paper proposed an on-device incremental learning framework that combines TCNs with an online learning algorithm based on backpropagation. This framework allows the gesture recognition model to be updated continuously with newly acquired data without retraining the entire model from scratch. The proposed method is evaluated on the NINA-Pro database. The results demonstrate that the incremental learning framework effectively adapts to time variability in SEMG signals, achieving improved performance compared to a static TCN model and other methods. All right, that's all from me. Thank you for your attention.